Hi, good morning or afternoon, everyone. I want you to think about a single word, legacy. Today, our legacy isn't just made of physical assets. It's a vast universe of digital information, our passwords, our documents, or even our cryptocurrency keys, an entire world of critical data. Today, we're going to talk about the future of your digital legacy. We call it Zaphenath. So, first of all, who are we? The driving force behind Zaphenath is Arstevia, a research collective dedicated to building the next generation of decentralized infrastructure, founded on the pillars of privacy respecting automation. Our core team of contributors brings together the best of both worlds. We have Rui Vieira, our lead Solidity engineer, an expert in architecting secure and efficient smart contracts on the blockchain. We also have Pedro Caninos, our head of business development and strategic alliances, who is building the bridges between our technology and the global market. And lastly, we have me, João Zaniboni, the director of strategy and ecosystem growth, focused on ensuring our vision becomes a sustainable and impactful reality. Together, we are building the solution to a problem that affects every single one of us. And that problem is an avoidable question. What happens to your critical information when you are no longer here? So, where do your passwords go? What about the keys to your crypto wallets, which hold increasing value? Where are the digital documents that are essential to your family? Today, the answer is deeply concerning. We are forced to rely on traditional wills, but they are slow, inherently insecure, completely centralized, and worst of all, they were never designed for the digital world. Your digital legacy gets lost, locked away, or in many cases, it simply vanishes. That is a risk no one should have to take. To solve this fundamental failure, we present Zaphenath, the deadman switch on blockchain. Think of it as an autonomous digital vault. It only reveals your information to the people you have designed, and only under the exact conditions that you have predefined. It's like a failsafe that works even when you can no longer operate it. The name was not chosen by accident. In ancient Egypt, Zaphenath Paneah was the name the pharaoh gave to Joseph, and it meant the one who reveals what is hidden. That is precisely what we do. We reveal what is vital, but only to the right person at the right time. And here we also present our logo with the Z stylized as an hourglass. It symbolizes exactly that, the passage of time and the guarantee that your legacy will be transferred securely when the sands of time have passed.
Hmm. Hi, my name is Pedro Caninas, Head of Business Development and Strategic Alliances. How does Zafina work? We have three basic steps. First, you create a key, then you associate it with the encrypted data you want to protect and release, and finally, you configure a timeout window that you have to be inactive to release the data. The way you maintain yourself active is through pings. As long as you are giving pings to the blockchain, the data stays private. The ping you give can be personalized to satisfy your needs. Ping while you're online, ping when using a system, ping when delivering a file or a project, or even integrating it with your own system, letting you customize the ping at will. If your pings take more time than the timeout window configured, custodians with appropriate permissions can access the data. And where Zafina can help you? You can use it as an individual and secure crypto wallets, social media passwords, and blessed wills and testaments. As a business, you can secure credential of critical systems and succession information and let it be shared with associates, shareholders, and managers, given your business stability. You could also use Zafina to secure legal agreements and conditionally release information if one of the parties fails to meet the deadline. And why choose Zafina over traditional non-blockchain solutions? The smart contracts can give you the trust of execution without the need of failable third parties. You would have the safety of data encryption, and you will also have the auditorship and transparency because all rules and transactions are public and verifiable. Also, you would have full control over the rules and data you put into the blockchain.
Let's take a look at our technology stack and a simple usage of our contract. We created a smart contract in Solidity. Our smart contract works in Ethereum compatible blockchains. And the idea behind the smart contract is a key-based secure storage and a ping mechanism for inactivity. The idea is that the user creates a key and associates with that key a sensitive data, a timeout, and some configurations that we cover in the documentation. And the user pings our smart contracts to signal for activity. So if the user fails to ping the smart contract for more than the specified timeout, the key data becomes readable. And we can use the key-based secure storage and the ping mechanism to check for inactivity and then release the key data in the specified timeout. And we also created a Rust application to interact with our clients or with our contract. So we use the Web3 crates to communicate with the smart contract, and our Rust client interacts with the contract, creating, deleting, updating, and reading the keys and keeping track of all the necessary data in a config file. And we also can start a daemon in our Rust application to ping the keys periodically. So we can start a daemon that reads the keys from the config file and pings the keys periodically to avoid timeout. We'll follow the usage example in the documentation to show you how you can use the Zaphenath smart contract with the Rust CLI client. So here's a brief summary. We'll first start a local testnet, deploy the contract and manage private keys, and we'll initialize a config file for the Rust client that we'll use to store keys and things like that. And in the step 5, we'll create a key on chain, and right after the creation, we'll try to read a key, and that should fail because we just created the key. We'll wait for the timeout and try to read a key again after the timeout, and we should get a success in this step 7. And after that, we'll start a daemon. The daemon from the Rust client pings the key periodically. So the daemon is pinging the key, and we should not be able to read the key content. So we'll test this behavior on step 9. We'll try to read a key while the daemon is running, and that should fail. And we'll stop the daemon in step 10 and try to read a key again after the timeout. And stopping the daemon, we stop the pings, and the key is available right after we stop the daemon. So right after the timeout, after we stop the daemon. So we should obtain a success on step 11. So let's start here on step 1. I have the command here on my terminal, so let's run the local testnet using Anvil. Okay, the local testnet is running, so I'll execute the commands from steps 2 and 3 to manage contract addresses, deploy the contract, and manage private keys. So I have the commands here on my terminal. Let's execute. Okay, we deploy the contracts, and in the step 4 we should initialize a local configuration file. So with this command from the CLI clients, we start a config file. Okay, we created a config file, and here on step 5 we create a key on chain. So we'll create a key with this data, that beef cafe babe, with a timeout of 10 seconds. So after 10 seconds of inactivity, we should be able to see the key contents. but we will try to read a key right after the creation. So on step 6. So on step 6 we should not be able to see the key content. So let's create a key. Okay, we created a key. Let's try to read the data, and we get data not available before timeout. We were expecting this error because we just created the key with a timeout of 10 seconds. And after 10 seconds of inactivity, remember we are not pinging the key, so the contract is detecting inactivity. So we now should be able to see the key data. Okay, we are able to see the key data, but we will run the daemon and start pinging the key. So let's run the daemon. We'll run a daemon with an interval of 5 seconds. So after each 5 seconds, the daemon pings the key, and while the daemon is running, we are not able to see the key content. So let's run the daemon. So we got the first ping here. The daemon is pinging the key after 5 seconds. So we got 2 successful pings here with the transaction hash. So the daemon is pinging the key, and the key has a timeout of 10 seconds, and the daemon is pinging the key at each 5 seconds. So let's try to read the key content here. Okay, we try to read the key content and we get data not available before timeout. That's the expected behavior because the daemon is running and the key is being pinged. So in the step, that's the step 9. And in the step 10, we'll stop the daemon. Stopping the daemon will stop the pings. And after 10 seconds of no pings, the smart contract sets the data as public, so the data becomes readable after 10 seconds without ping, as we said here, a timeout of 10 seconds. So let's try to read the key data again. So we can see the data here, and this shows the correct behavior of both the Rust CLI clients and the smart contract. We cannot read a key when the expected timeout hasn't passed, and with the Rust CLI clients we can successfully execute commands such as read key or run the daemon or create key and create config files. So both the contract and the client are working well.
Thank you so much for giving us the opportunity to show our solution. If you have any questions or suggestions, please scan this QR code. If you want to explore more about the technicalities of Zaphenath, please visit our website and GitHub. And that's it. Thank you.